So now let's talk about critical points. So if you remember from Calculus 1, critical points are points where your derivative is 0 or undefined. And we're going to have something similar happen here, but we have to talk about partial derivatives. So let's start by defining what a critical point is. So we're going to suppose that f, it's a function of two variables defined on an open region R containing x naught, y naught. We're going to say the point x naught, y naught is a critical point of f if one of the following is true. So either your partial derivative with respect to x is 0 at your point, and your partial derivative with respect to y is 0. So this is an and. Both of those things have to be true. Or one of your partial derivatives does not exist. So why do we care about critical points? What's the point, I guess? So the theorem 13.6 from your book tells you if f has a relative extremum at the point x naught, y naught on an open region R, then this point is a critical point of f. So all of your relative extremum correspond to our critical points. So it gives you a place to look to find relative extrema. If I look for critical points, those could possibly be extrema. So let's look at our first example with critical points here. Determine the relative extrema of the function 2x squared plus y squared plus 8x minus 6y plus 20. So we're going to start this problem. We're going to start by finding the critical points of f. And so in order to do that, I need my two partial derivatives. I need fx, take the derivative with respect to x, you'll get 4x plus 8. And fy, the derivative with respect to y is 2y minus 6. So the first thing to notice is that these two functions here, these are defined for all x and y. It's because they're polynomials. So the only critical points I get are from the derivatives being 0. So what you need to do now is you need to solve 4x plus 8 equals 0 and 2y minus 6 equals 0. So what we have going on here, this is a system of equations. So you need to solve for x and y in the system of equations. Well, it's pretty easy. You can solve for x in the first one. X will be -2. Solve for y in the second one. Y will be 3. So we get one critical point. We get the critical point, -2, 3. Now, just because you have a critical point doesn't mean you have a relative maximum or minimum. So we need to ask ourselves, is this critical point a relative extrema? Well, to answer that question, we need to look back at our function. It was 2x squared plus y squared plus 8x minus 6y plus 20. And what we're going to do is we're going to rewrite our function. We're going to complete the square here. So I'm going to group up my x terms, group up my y terms, and I'm going to factor out a 2 here. Okay, now I'm going to start completing the square. So if I take half of 4, 2, square it is 4. So I'm going to put in a plus 4 here. But what did I really add in? I added in an 8, so I need to subtract an 8. Take half of -6 is -3, square it is 9. So I need to add 9, but then I need to subtract 9 as well. So now, this is 2x plus 2 squared, y minus 3 squared, plus 3. If you plug in our critical point here into our function, you would get 3. And if you plug in any other point other than our critical point, so if xy is not equal to -2, 3, well, if you look on this right-hand side here, you'll see that you'll get a number bigger than 3. Then f of xy will be bigger than 3, because these first two entries here, these are squares, so they'll be bigger than one of them. At least one of them will be bigger than 0, and so overall I'm getting something bigger than 3. So what this tells me is that my point, my critical point, has to be a relative minimum. So we have a relative minimum occurs at -2, 3, and the relative minimum, the value is 3. So my relative minimum occurs at this point in the xy plane, and there's my relative minimum value.